Hey guys, welcome back to Genius Learning. All right, so this last segment, we're trying to find now the total potential. So we want the total potential, okay? And it's confusing because we found the potential inside and we found the potential outside separately, but we can't put them together and say that's the total potential. Okay, and I'll explain why. Also, I wanted to put here, this is what we found for the electric displacement in the previous videos. This is the electric displacement, the inside, and electric displacement outside. So for the total potential, okay, I'm gonna draw a sphere here and let's take a look at what we mean. So for here, separately, what we did was we had a sphere and we wanted to check the inside. So we went from the shell, which was a length of A, towards the inside to a length of R, some radius R. So that's why our integral had A and R in it, and we end up with an A and R here in our answer for the potential in the inside. For this example, right, we have the same sphere and we wanted to check somewhere outside. So now this is our A, which is on the surface, but our R was somewhere out here. Okay, and potentials work from the outside in. And so some outside distance, infinity, goes in towards the R, and our integral was from this is final would be R, initial would be infinity. Okay, so this was the important integral to look out for there, and for this one we had our final is going to be R and our initial was going to be A. So this was the radial integral. Okay, so you can see the difference. Now what we're talking about when we're looking at total potential is we're going to start, we want some R in here, okay, like that. So in order to get to this R, right, we have to start from the outside. So from some distance infinity, like we did here, except here we stop at a value of R because we're checking outside, right? When we're checking the total potential, so we want the total potential, meaning R is in here, we're gonna go from an infinity all the way to the shell, and then from the shell to that R. So we're gonna have the first integral. See, I'll write it out. Okay, so we're gonna have, let's see, okay, I'll write it here. We're gonna have our first integral, so it's negative, right? It's gonna go from infinity to A, right? And then we're gonna put the electric displacement that we found for that region, which is outside, and the permittivity that corresponds to the outside, okay, dotted with DL, minus, so we're gonna add them, but since the equation is already negative, we're subtracting them. So, but really we're adding everything coming inward. So minus, and now we go from A to R, what we're interested in. Okay, so we're gonna go from A to R, and again we have electric displacement in that area, permittivity corresponding for the inside, and then dotted with DL. Okay, so this is now the new potential integrals that we're interested in. And the main difference from this and adding up these two together is that this integral, when we were inside, is fine because from A to R, right, A to R, everything is gonna remain the same. Even the permittivity, we know the dielectric constant in there is some value, so we represent it like this, that's fine. But for this integral here, that is from the outside, this one is different. Because here we did an integral that went from infinity to R, right? Because that's what we were looking for, some R value outside of A. But now when we do the total, we always go up to the shell. Always go up to where the first concentric circle or the first layer hits. You're no longer looking for a random r out there. So this is the main integral that messes up us just adding these two together. Okay, so let's try to figure these out. And we have potential, infinity, and A, right? What is the electric displacement outside, right? And the electric displacement outside is here. Okay, we have rho naught A to the third over 3r squared. Okay, and we have our epsilon naught. Let's just leave it for now. And let's see, we got dr. So right now I'm just gonna fill everything in, but we have to change this. So then we have the integral from A to R. What is the electric displacement inside? So we already know what it is, but we have the answer for this integral right here. But I'm just gonna go through the steps to show you that it's the same thing. So the electric displacement for the inside is this. So we have rho naught R over 3. Okay, and then we have here epsilon. We're just gonna leave it there, and dr. Okay, so we have this. Now let's simplify this a little more. So this epsilon, right, is for the outside. And what do we know for susceptibility, electric susceptibility outside? It's 0. So chi outside is equal to 0, right? Therefore, Ke equal to 1 plus chi, this is 0, chi is equal to 1. I mean, Ke is equal to 1. So when we change epsilon to Ke epsilon naught, this goes to 1, and epsilon just turns into epsilon naught. Okay, so this one here is going to turn into epsilon naught. So let's do that. We got negative. Let's take a few things out. Let's take the rho naught A to the third over 3. And this epsilon turned into epsilon naught. We could take that out. And now we only have an integral from infinity to A. R squared is on the bottom, so it's right r to the negative 2 dr. Okay, so we have that one set up. And then here we have, let's take things out, and we're gonna have rho naught over 3. And what happens to this epsilon here? So this is inside the material, and so inside the material we know that epsilon, the absolute permittivity, is equal to Ke epsilon naught. So that's what we're going to change it to, this right here. So it's right here, Ke epsilon naught, and then let's write the integral A to R. What's left over is R dr. Okay, and now let's evaluate the integral. So this integral here is going to be, let's see, we got, if we just evaluate the integral, it's going to be negative 1 over r evaluated from infinity to A. And here, if we just look at the integral, we're going to have r squared over 2 evaluated from A to R. Okay, so let's write that out. We got, let's see, let's push this up a little bit. Okay, we got that the potential is equal to negative rho naught A to the third over 3 epsilon naught. In here, we're going to have minus 1 over A plus 1 over infinity, right? Minus and a minus plus. This goes to 0. So over on this side, we're going to have negative rho naught 3 Ke epsilon naught. And I should move this 2 outside. So I'm gonna change this into a 6, right? 2 times 3. And we're gonna evaluate this. It's gonna be r squared minus a squared. All right, and one last trick or simplification. Let's erase these lines here. Okay, so one more simplification. We're gonna put, well, this negative and this negative right here cancel. And so we see that we're gonna have this A cancel with one of them up here. And so we're gonna have the potential equals a positive, right? Because this negative cancel. We're gonna have rho naught A squared, because this was to the third, there's an A down here. And then this is over 3 epsilon naught. Okay, so that one's good. And here, I'm gonna distribute this negative in so I could rearrange the A squared and the R squared, just to have everything positive. So rho naught over 6 KE epsilon naught. And then since I flipped these, I got A squared minus R squared. Okay, and we can leave it there, but we have a final expression. Okay, I'm gonna move this up a little bit just to give me some room to do the last part. Okay, so this is the potential. This is the total potential. Completely correct, right? But let's simplify it or rearrange it so that way we can work with it for the final question, which is what is the potential at the center? Okay, so the last question is what is the potential at the center of the sphere? All right, so this is the total potential, right? We got it from evaluating outside all the way in. And let's just rearrange it real quick to make our final evaluation even quicker. So I'm gonna take this answer, right? I'm gonna pull out, let's say, the rho naught and A squared. Maybe let's not move that fast. Let's pull out 3, right? 3 and epsilon naught. And that's it. So now what we have left in this first one is A squared, right? Plus, if we pulled out a 3 from the bottom, we'll have a 2 down here. So 1 over 2, the KE stays, right? The epsilon naught came out. And in here, we still have A squared minus R squared. All right, and now we're gonna do, give me 1 second. Sorry about that. Oh, sorry about that. Just running out of battery here. Okay, so the last part here, we're gonna rearrange this and we're gonna take out an A squared from this side over here. So just algebra, we're gonna take out an A squared from everything. So rho naught over 3 epsilon naught. If I take out an A squared from everything inside these parentheses, what I'm gonna have left in these parentheses in this spot is 1 plus this term here, if I distribute it in, has an A squared, so that's gonna be fine. This is gonna be 1. And then minus this term right here did not have an A squared, so we're gonna put an A squared on the bottom. So if we factor it back in, it goes away and we retrieve the R squared that we had left. So this expression here is a little bit easier for us to evaluate the potential at the center. Okay, and so now the final part, right, the potential at the center means that at the center of the sphere, right, r is equal to 0. So all we have to do in this expression is make r equal to 0, and everything else will be what we have for our potential at the center. So rho naught a squared over 3 epsilon naught. We got 1 plus 1 over 2 ke, and I think that's it. So you see, we got rid of that whole side over there, and this is what we have for the final expression for the potential at the center. Okay, so something to look out for is going to be thinking that finding the potential on the inside, finding the potential on the outside separate, you can add up to give you the total potential. So always look out for these integrals, because these are the ones that, you know, throw off the whole problem. Then once you find the total potential, you have to understand where you're at as far as the material goes. The permittivity is different whether you're outside or inside, so take that into account. See if your susceptibility is 0. And then once you have your potential, if you have to find the potential at the center, then that just means that r is going to equal 0. All right, so maybe you rearrange what you have to simplify your life, and this is going to be the expression for the potential at the center. All right, so it's a pretty long problem, but I think it was very detailed in a lot of things that you're going to need for E&M, especially for this chapter. All right, so hope you enjoyed it. Thank you guys for watching.